Hello everyone, my name is Rajoshi Roy and today we will be talking about Linear Quadratic Gaussian Control, the LQG control. So we'll be looking into the LQG, why do we use LQG control, the deterministic LQR control, LQR regulators, the observer in a noisy system, the so-called Kalman filter, and we'll be looking into some of the examples of the Kalman filter in the Simulink. Then we would go ahead and look into the linear quadratic Gaussian optimal control, and we'd be talking about the limitations of the LQG. Okay, so any system in its general state space form can be represented as x dot is equals to ax plus bu, y is equals to cx plus du, where x is the state vector, y is the output vector, u is the control vector, and A represents the state matrix, B represents the input matrix, C gives us the output matrix, and D is the feed-through term. If our system is both controllable and observable, then we can design a full state feedback for the system that will stabilize our system through the pole placement at the desired locations on the left-hand side plane of the S domain. So in that case, it is possible for us to design a feedback controller, which is given by the form u is equals to minus kx for our system to stabilize our system and to get a better performance. Then, what's the purpose of using an LQG regulator? Well, we know that the LQR is an optimal regulator for a state feedback control system, and it works well only under the deterministic environment where the process and the output states are basically not corrupted by any noise, from which we can get the accurate measurements. But what if the process is operating under some noisy environment, just like in a real world scenario, and the output measurements are somewhat non-deterministic in nature too? And in that case, we use something called the linear quadratic Gaussian regulator and Kalman filter to control our system, which is operating under the stochastic or the noisy environment. Now, talking about the LQR control, we know that the LQR control gives us the optimal feedback control K, which balances the feedback, which balances the regulation performance, that is how fast we want our system to converge, and the control effort that we are going to spend on the control of the system for controlling our system. So that gives us, K gives us the optimal gain that would balance both the things. And so the basic purpose of the LQR problem is to find the feedback gain that will minimize the quadratic cost function, which is given as J is equals to x dot x transpose q x plus u transpose r u, where q and r gives us the weighted matrices for the penalty, which represents the penalty for applying the state regulation and the input and the control inputs. So what happens in the real environment is that all the measurements that we take in the real environment are somewhat corrupted by the disturbance that is associated by the process. Sometimes the measurements that we take from the output are also corrupted by the noise sensors from the noise that we are measuring the output from. So in that case, we don't have the full knowledge of the states of our system, and also the measurements that we are taking is also corrupted by some noise as well. And in these kind of situations, we would have to develop something which can not only estimate but would also take control of the noise that is associated with the measurements as well. So we use a Kalman filter to filter out the disturbances and predict or estimate the best measurement values for our system when the system is operating under noisy conditions. So a Kalman filter is an observer, basically, which we can employ in any real world situation to predict or estimate our measurement values. A good example of the Kalman filter can be given by the self-driving car or self-locating car, which locates itself through GPS. For example, let's take an example that there is a self-driving car competition, and our car has to travel in different terrains for 1 kilometer, and it has to reach the finish line, and it has to stop at the finish line under different terrains, and the winning team would be the one that has the car which stops very much accurately as the finish point reaches. So that we can say that the average final position or the location per variance of the positions of the different of the car under the different scenarios are should be really less, and it should be around the final position of the competition. So from this graph, we can show that what our car dynamics is for a single state system. And this shows our process and the measurement noises are a Gaussian distribution, as we can see with a covariance of sigma W and the sigma V. Okay, so what Kalman filter does is that it computes an optimal estimate of the car's position with the minimal variance. This is formed by multiplying the prediction and the measurement probability density functions together and finding the mean of the resulting probability density function, which we can see from the graphs here on the right hand side. The Kalman filter is multiplying the variance, the probability density functions of the measurement and the prediction, and the resulting graph, and the mean of the resulting graph represents the Kalman filter's gain, the prediction from the Kalman filter. Looking into the next slide, we can see that computationally the Kalman filter can be shown as a state observer under a stochastic system. The Kalman filter has two parts. It has a state prediction part and a measurement part. So the first part, the state prediction part, is used to calculate the state estimate and the error covariance matrix P. The error covariance matrix gives us the uncertainty in the estimated state. This variance comes due to the process noise and the uncertainties in the measurements in the state measurements. The estimated state is then used to find the updated state estimation and error covariance, and the Kalman gain is then computed such that it minimizes the error covariance P. We can also use multiple sensors to get our state measurements accurately. Now we would show how we can implement the Kalman filter in the example of a pendulum's angular position in determining the pendulum's angular position in Simulink. So we can see that from the picture here that the linearized state equation can be represented by the equations that is given down below. And this is for the small angular value of theta that we can linearize the system around the origin. Now we have built the pendulum model in the Simulink, and it has two inputs. The first input is the torque input, and the second input is the process noise that is going into the pendulum block. And The pendulum block's output is the angular position, which we would measure with a sensor, but our sensor's reading has some noise in this case. Now we have the actual measurement. Now from the block diagram, we can see that we have our actual measurement, which is going into the Kalman filter. There is the actual measurement, and we have the measured value, which is coming from the pendulum block itself. So the Kalman filter blocks takes in the measurement, the system model, and the input to generate the optimal state estimation. Also, the Kalman filter doesn't know the exact initial conditions. For our case, we'd be taking the pendulum's initial angular position as 10 degrees, which is really a small value of theta, for which we have got a linearized model of the pendulum system. Now, looking into the results for the system, we can see that the Kalman filter has done a great job in in predicting and estimating the state theta. As we can see from here that the actual theta is shown in the green line. The orange graph shows the noisy signal, and the estimated value of theta is shown in blue. So all of those things lie on top of one another, which shows that the Kalman filter has done a great job in correctly predicting and estimating the actual state theta of the pendulum system. Now, what happens when the initial position of the theta goes very large? Well, what if we take the initial angular position of the pendulum to be 60 degrees? In that case, we can see that the system is not behaving totally or completely as a linearized system now. And in that case, the Kalman filters, we can see that the Kalman filters estimation is somewhat irregular and it's not matching up with the actual theta values. So we can say that in that case, we can say that the Kalman filters works very well in when the system has a linearized model, but it can be a little bit, it can give us wrong results or wrong estimations, under the situation when the state is when the system has some non-linearities associated with it. All right, so what is linear quadratic Gaussian optimal control? We have seen that in the previously that we have built our Kalman filter and we know what LQR regulator is. So when we combine both of those things into our system, that system can be called as the linear quadratic Gaussian optimal control system. So the best thing here is that we can design our Kalman filter separately and our LQR regulator again separately, and both of those things can be designed optimally in a separate way. And then even if we combine both of those, the whole system remains optimal. And that is the best part of it. And this happens due to the separation principle. Mm, uh, Separation principle associated with the mathematical calculations of the state space. Okay, the LQG control again can be defined in a way that now we have our process noise and we have our measurement noise going into the plant, and the process noise is going into the plant and the measurement noise is corrupting the output values which is coming out of the plant. So under these situations, when the system is operating under noisy or stochastic environment, we can use the Kalman filter to correctly predict the estimated states of the system, and we can use the LQR as a feedback regulator to place our poles of the system at the desired location. And in this case, we have used the the process noise and the measurement noise are Gaussian white noise processes with a variance, with a covariance matrix sigma W and the sigma V. So our aim here is to get a regulator which would minimize the quadratic cost function again, but here the quadratic cost function is expected value of the expected value as we can see here from the diagram. Okay, so we have done some LQG design in the MATLAB, and we have used in the we have built a system with the ABCD parameters, and then we have built a system SYS is equals to state space with the parameters ABCD. Then we have defined our weighting matrices and the noise covariance matrices, and then we have built our LQG regulator by using the code LQG, and that builds our LQG regulator game for the system. And here is the results that we get from the by operating that LQG by using that LQG command in the MATLAB. So we can see from the LQG block diagram as well that it has two components again. It has the Kalman filtering, which operates, which takes in the measurements which are corrupted by the noise, and then it is used to correctly predict or estimate the correct values of the state, which goes into the LQ regulator again, and then the LQ regulator is used to place the poles of the plant at our desired location. And under this system, the plant is having a process noise, and our measurements are corrupted by the measurement noise, which is coming out of the plant. Okay, so uh, we can see that we are using both the goodness of LQR and the Kalman filter, which is LQE, the linear quadratic estimator. So what are the limitations of LQG optimal control? Well, the LQG control is inherently suffers from robustness issues. It is in fact less robust than LQR. While LQR has impressive gain margin of infinity and the phase margin of 60 degrees, it is guaranteed in an LQR, but there is no guaranteed stability margin for an LQG control. The closed loop system can become unstable if our Kalman filter is not designed properly to take control of the nonlinearities in the system. So LQG control can have several limitations over LQR if the system has nonlinearities associated with it. Okay, so that's it for now, and thank you all.